Hi class! In this video we go a little bit further than the basics of sets, but we talk about more notation and what exactly is a subset. Let's get started. So we begin with some notation. We say that set A and set B, so we write them again with the nice capital italicized A and B. We say if we have sets A and B, then A is called a subset. I'm going to fill in my first blank here. You can too. A is called a subset of set B. And here's how we write it. Ready? We write A first because A is a subset of B, and then we use this symbol. It looks kind of like the letter C, but it's more like a horseshoe, okay? And then underneath it, we put a line, okay? So that looks a little strange, but maybe to some of you, it reminds you of like a greater than or equal to symbol, right? So this is the symbol that we use for subset. So on your note card somewhere on your notes, I would write subset symbol is the horseshoe going to the right with the line underneath it. So we say A is a subset of B. Now, when is A really a subset of B? Let's get the definition. Here it is. If every element of A is contained in B. Okay, so let's think about this for a moment. Notice how I said that that horseshoe kind of looks like the letter C? Just a fun little way to remember the meaning here. C is the first letter of the word contained, right? So if A is a subset of B, what we're really saying is every element of A is contained in B. For example, consider the set 2, 4, 6. That would be contained in the set 2, 4, 6, 8, right? So A would be a subset of B. All right, back to our notes here. Now notice in the notes here that it says they may be equal. Now that might just blow your mind, right? So if I say A is a subset of B, I thought A had to be smaller than B. Not necessarily. Notice that little equal sign kind of looking thing underneath the horseshoe type of thing? That's really saying A is contained in B or A is equal to B. So notice that is an option. Okay, another important fill in the blank here. For a finite set containing n elements, so n is just an arbitrary number, it could be 3, 5, however many elements, there are how many possible subsets of that set? Okay, this can sound a little confusing, all right? So I'm going to give you a real life scenario. Let's say, for example, you have 2 kids, okay? So this is the set of somebody's kids. We'll call it set A. And their 2 kids' names are, let's say, Joe and Sue, all right? I like short names so I don't have to write as much. All right. So let's say those are the 2 kids that someone has, and that's the set with 2 elements inside. So here we would say that the number of elements, the cardinal number, if you remember from our last video, of set A would be 2, right? So there are 2 elements in this finite set. So if someone said, how many subsets could you form of set A, we need to figure that out. So before I just give you a formula, let's see if we can explore together how we can make subsets. So one way that we could think about subsets is you're going to take a subset of them and maybe take them to a theme park, right? You tell your 2 kids, Joe, Sue, I'm going to take a subset of you to Disney. Oh, they're very excited. But wait, if they understand subsets, they might not be going to Disney. Let's see why. So what are the possible subsets? Well, couldn't you just take Joe? Well, let's think about it. Is that set contained in set A? Yeah, Joe, the set containing Joe is found in set A, right? Because every element from this set is found in set A. So that's a subset. Let me get some space here. What's another possible outcome here? Instead of just taking Joe, we could just take Sue. Okay, so that's another option. Okay. Is there any other possible subsets, any other options? If you say, I'm going to take a subset of you to Disney? Well, you could take both of them. Maybe that would make both of them happy. Maybe that would make your life a little harder. I don't know your kids, okay? Well, there's one more option that neither kid will like, but maybe you will, or at least your pocketbook, okay? You could take neither one. Now, I wouldn't recommend posing the scenario to your kids that way, but that is a possible subset, right? You could take none of the items from that set. In this case, the items are your kids, okay? So how many possibilities were there then? No items, 1 item, or both items. So in general, not in general, but in total, we had how many subsets that were possible? 1, 2, 3, 4. So in this case, there were 4 possible subsets for a set with how many elements? 2. I wonder if there's a pattern there. If I threw in another kid into the mix, maybe we had a 3rd kid named Max. Well, now you could take all 3 of them. You could take 2 at a time. You could take 1 at a time, or you could take none of them. And when you add that up, I encourage you to pause the video and go ahead and add that up. See what you get. Did you get 8? I wonder why. Well, I don't actually wonder, but you might be wondering why. And the reasoning is, for every element of the set, you have two choices when you're trying to make a subset of that set. Do you take them or do you not? So if you have two choices for each item, 2 for this one, 2 for this one, 2 for this one, if you multiply 2 times 2, you get 4 in this case. If you had 3 elements, 2 times 2 times 2 is 8. If you remember from algebra or your previous math classes, when you multiply by the same number over and over again, that's also the same as taking that base and raising it to a power. So in this case, the equation is, oops, wrong place. Let's go back up here. 2, make it my color, 2 to the power of n, where n is the number of possible elements in your set. So in the case where I had 2 elements, I would say that there are 2 to the second, right, which is 4 possible subsets. Okay. Now, you may agree or disagree. You might not like the definition of subset, but this is the definition of subset, okay? There are, in this case, 2 to the n possible subsets for any set with a finite number of n elements. Let's go ahead and erase some of that work, so feel free to stop and make sure you got it all written down before I erase this from you. All right. And now we're going to look at another example on the screen with 3 elements. And this might be really easy based on our discussion that we just had. In fact, I hope it is a little easy for you. Take a look with me. It says, for example, if set A has the elements 1, 2, 3, so it's just in roster notation, braces, 1, 2, 3, close braces, then we know that the cardinal number, or n of A, of set A, equals 3, because there are 3 elements, right? So how many possible subsets would there be? We said 2 to the 3rd power. So 2 to the 3rd power is really 2 times 2 times 2, or 8. Remember, that's not 2 times 3 when you have a base to a power. It's 2 times itself 3 times here. So there are 8 possible subsets. Now, of course, you could list them, right? You could have all 3, 2 at a time, 1 at a time, none of them. Okay, so that would be the answer there. Well, let's look at a real-life scenario here involving some of my favorite things, pizza. Okay. So for example, let's say we have a pizza shop that's offering the following toppings. So they don't have that many in their inventory. They just have pepperoni, bacon, ham, pineapple, and sausage. So if a person is going to order, the question here is, if a person may order as many or as few toppings as they wish, there are how many possible pizzas that they could order? Okay, so they can order as many or as few toppings, meaning they could order all. How many toppings are there, by the way? Pepperoni, bacon, ham, pineapple, sausage. 5, right? Okay, so they could order all 5 toppings, or they could order 4 of the toppings, or 3, or 2, or 1, or what's the other option? Yeah, kind of boring, but no toppings, right? So in this case, we would say this is really a set, isn't it? We could say this is set A, where the set contains the elements pepperoni, I'll shorten it with pep, bacon, I'll shorten it with bake, ham, pineapple, I'll just say pin, and sausage. Okay, I'll say saw. All right, so we have a set with 5 elements. So here n is 5. The number of elements of the set is 5. The cardinal number is 5. So the number of possible pizza orderings, assuming that you could order as few or as many toppings as you want, of course you'll pay more probably, is 2 to the 5th power. And again, you're welcome to use a calculator. Any scientific calculator would have a power option for you. Or you could multiply 2 times 2 times 2 times 2 times 2 5 times. And you should get 32. So there would be 32 different pizzas. So if someone comes up to you, by the way, let's say you're on a date with someone for the first time, and they say, that's exactly the same pizza I would have ordered. Well, there was only 1 out of 32 possibility of that. That might not be accurate. Okay. Finally, one more note to this slide before we go practice. We say that the empty set, remember that's the set with the braces and nothing inside. It's also written as the circle with the line through it. The empty set, this is really important to put in your notes. I'll put a little star and another star just to make sure you see it. The empty set is a subset of every set. What does that mean? Well, when we think of subsets, remember what we're talking about. We're saying, how many ways could I pick elements from the big set to make new sets, right? And what is one option that is always on the table? Back to the theme park example, the option that your kids do not want is that you don't take any of them, right? So the option always is there to not choose any of the elements from the set, which means the empty set is always a possibility. All right, so with that in your notes and with that in mind, let's head to our next example. Proper subset notation. So we're about to get very fancy, okay? What is a proper subset? Well, it's kind of like how you would like a subset to be defined. Let me get into it. Consider sets A and B. We say set A is a proper, I'm going to fill in my first blank on this slide. You can too. We say set A is a proper subset of B, and it's written this way. Notice it says A, and then it has that horseshoe-looking symbol to the right. A is a proper subset of B if every element of A is contained in B. Well, that sounds familiar. It kind of sounds like the subset definition. That's right. But notice here, this is an important part. A, look at that symbol. It means does not equal. A does not equal B. So here, this is the proper definition of a subset. So to be a proper subset, not just any old subset, but a proper one, you have to have every element of A contained in B, okay, just like the subset, but with the extra added qualifier that A cannot equal B. In other words, if you want to put this in another way, you could say there have to be fewer elements in A than there are in B. So for example, if I had the set with the numbers 2 and 4, that would be a proper subset of the set 2, 4, 6, right? Because every element in A is found in B, and A has only 2 elements, whereas B has 3 elements, right? So that would be a proper subset. Notice if I put the line underneath that horseshoe, now it just says subset, which is also true, right? So every proper subset is by definition a subset, but not every subset is proper. That's a little bit of a grammar tongue twister there. All right, let's take a look at the rest of this slide here. Let's fill in some more blanks. For a finite set, so in this box we're talking about a finite set containing n elements, okay, a finite set containing n elements, there are how many possible proper subsets of that set? How many possible proper subsets? Well, if we think back to our previous slide, feel free to pause the video, go to your notes. Remember how we figured out how many possible subsets there were? We said for every element of the big set, you can either take it or leave it, right? So there were always 2 options, and then you multiply 2 times 2 times 2, however many times there are elements, right? 2 to the n. But now, if we have to only talk about a proper subset, there's one condition that's not allowed, and that was that the set A cannot equal the set B. In other words, you can't have the entire set of items as one of your proper subsets, because then they would equal each other. So there's one fewer. 2 to the n tells you how many subsets there are, and I'm going to make another color change on you, then subtract 1. So 1 fewer than the number of subsets, that's how many proper subsets you should have. Let's see if we can do an example here. If set A contains these people, Bo and Ty, so 2 people, so then we know that there are 2 elements in that set, how many possible proper subsets of A would there be? Proper subsets of A. Well, again, we can do all the listings, right? We could say, well, we could have Bo by himself, okay? Or we could have Ty by himself. Or we could have nobody. Or we could have Bo and Ty. This is how we performed our subsets last time, right? One person, nobody, both people, right? But in the case here where we're talking about the specific word proper, what has to be true? The sets cannot be equal to each other. So wouldn't this set here, Bo and Ty, be the same thing as this set here? It would. So we have to exclude that one possibility. And that is why instead of 2 to the second, that's how many subsets there would be, right? Number of subsets, there would be 4, right? But we'd go 4 minus 1, or there are 3 possible proper subsets. And that would be nobody, just Bo, just Ty. Okay, so that's what we mean by proper subsets. It's all of the possibilities except for the one where we take everybody, basically. All right, some other notation just to review here we've already used. Maybe you can see if you can pause the video and write down what you think each of these symbols means. What was the first one? Element, good job. What was the next one? Not an element, awesome job. What was the next one? Subset, almost. Proper subset, that's what I wanted to hear. Proper subset. What do you think the next one was? The horseshoe with the line through it. So not a proper subset. And below that, what do you see? You see subset. And if you see one below that in your notes, it would probably have a line through it, and it would be not a subset. Okay, so make sure you have in your notes somewhere, very well organized, all the different types of symbols helping to relate elements and subsets. Well, let's head to our next example, shall we? Example 1, true or false. And in part A, we have A through F here. In part A, it says the set, and then in roster notation, it lists lion, comma, tiger, comma, bear. So here we're talking about the set lion, tiger, bear. Well, think to yourself, how many elements are in that set? 3, good job. Okay, now let's take a look at the symbol we see. What does this symbol mean again? The horseshoe to the right, that's right. It means proper subset, right? So to read this in English, the way we would read it out loud is we would say, the set lion, tiger, bear is a proper subset of the set lion, tiger, monkey. Now, would this be true or false? Maybe you take a moment, pause the video, think to yourself, and then see how you did. How'd you do? Well, notice that these two sets would be what we call equivalent, right? We talked about this in a prior video because there are in both sets 3 elements. Would they be equal? No, because bear and monkey are different elements, okay? So the next question is, remember this symbol here, the proper subset means every element in this set here has to be contained in that set on the right. So every element on the set on the left has to be contained in the set on the right. Is that true? No, bear is not in that set. So that is a falsehood. So let me get red for false here to keep it easy for us to remember. False. Okay, let's head to our next example here. And before I do, actually, I want to make one little point. Notice, though, that even if this had said the line underneath it, right, that means a subset, this still would have been a falsehood because every element in A would not be contained in B, right? So that is the issue. But it could have been true if I had maybe added one more element to that set on the right. Maybe it was lion, tiger, monkey, bear. Now it would have been true in both the proper and the subset definition. Okay, so let me erase that line for your notes so you don't get confused. All right, let's head to B next. Here we go with B. It says the set with Italy as the only element is a proper subset, so same symbol again, is a proper subset of the set containing the elements Italy, Spain, France. Pause the video, see if you think it's true or false. What'd you think? Well, if you said true, then you are correct. Let me get a different color that will be our true color. We'll use black. Okay, so I'm going to say true. B is true. Why is that true? Because every element in the set on the left, so in that case just Italy, is contained in the set on the right. So that is true. Notice also the definition of proper subset requires that they're not identical sets, and that is satisfied here. So this is a proper subset. Let's take a look at C together. C says pink. Now notice something's missing. Pink is an element of, and then we have the braces again. Inside of this set, it says blue, pink, orange. So is pink an element of the set containing blue, pink, and orange? You can pause the video. You can tell me what you think. True or false? If you said true, you were right. Because notice how pink is found inside here. Now you might be wondering, wait a second. That sounds very, very similar to the last one, okay? Well, not necessarily this for the same reasoning, okay? So take a look again. Subset means every element of the set on the left has to be contained in the set on the right. Element means this particular element needs to be found inside of the set, okay? So it's a little bit different, All right, take a look at D with me and see what you think, if it's true or false. So in D it says, the set containing one element, the number 1, is an element of the set containing these sets. Kind of confusing. Brace 1, a set with braces around it with the 2, and then a set with braces around the 3, and then close the braces for the whole set. So notice here that the big set on the right has smaller sets as the elements. Okay. Now typically, you would expect to see one of these symbols here, a subset or a set symbol, when you're talking about two sets and how they relate to each other. Okay. However, because we did insert an entire set within a set, we kind of nested them like a nesting doll, then this is true. We see that the set 1 is an element of this set that contains the set 1, doesn't it? So this is another truth, but we need to understand why it's true. not just that it's true. And again, if any of these are confusing, always feel comfortable to reach out to me. I'd be happy to give you more examples. Let's take a look at E. Take a look at E with me. What does that look like? That's right, the empty set. And sometimes in your homework, they'll use the circle with a line through it. Remember, that's the same thing. Those are equal sets, right? As the set with just the two braces and nothing inside. They both mean empty set. All right, so let's take a look here. It says the empty set is an element of the set containing the elements 1, 2, 3. Okay, would that be true or false? You can look at your notes, so not judging. Take your time. If you said true, you're almost right. You were probably thinking of the fact that we had just made a big important note on the last slide that said the empty set is a subset of every set. So it's one of the possibilities, right? You can always take none of those items. But notice here, the symbol is not subset, but element. Element means what's on the left must be found inside of the set. So this is going to be a falsehood for that reason, right? Because notice you don't see the empty set inside of that set. If, on the other hand, I had used this symbol up here, the subset symbol, in that case the proper subset symbol, or even the regular subset symbol, then it would have been a truth. But as an element, it's not found inside, so this is a falsehood. Okay, one more. See if you can get this one. It's a little tricky. The empty set is a proper subset of the empty set. Huh. Well, you're probably thinking, I know this one. She just told me, right? The empty set is a subset of every set. Okay, yes, it is a subset of every set. But what is the definition of a proper subset, which is what this is? Because there's no line underneath it. It means every element on the left set in the left set has to be contained in the right set. And what's the other little caveat? They cannot be equal. So notice these are exactly the same. If there was a line underneath it like that, then this would be a true statement. But without that line underneath it, this is a falsehood because they are equal to each other. Remember that a proper set cannot have equal sets. Right? A proper subset, will not be equal to the original set. All right, so that was a little bit tricky. You might want to pause that one, go back, take your time with it. Make sure you ask good questions if there's anything confusing you, and we can clarify that before you go practice. It's better to not practice at all than to practice incorrectly. All right, so let's head over to our next example, shall we? Example 2, true or false? For any sets A and B, where A, what does this say? Does not equal the empty set. Let's pause for a moment and see if we understand what they're saying. So you have two sets A and B. Now, just to kind of visualize what's going on here, I'm going to use something that we'll talk about in future videos called a Venn diagram. In a Venn diagram, we usually make a rectangle. This is a really ugly rectangle, I apologize. And then inside the rectangle, we call the rectangle our universe. And we haven't really talked a lot about this symbol here. The bold, capital, italicized letter U means the universal set, or the universe of all possible elements. And so what they're saying here is, in your universe, assume that it's not empty. So assume that there's something inside. So I'm going to call this my universal set, okay? And inside of this universe, we might have different categories or sets, right? And so let's say we have set A and we have set B. What they're also saying is, let's assume that set A is not equal to the empty set. In other words, set A is not empty. It has some elements inside of it. And they also would like us to assume that A is inside of this universe, right? A is a proper subset. It's contained in the universe. So perhaps A looks something like this. Maybe this is my A. Maybe my B is over here. We don't know yet. If I wrote it like that, that would mean that they have nothing overlapping, right? They have no shared elements. Or I could write it something like you're more used to seeing, perhaps, where there's an overlap like this, okay? And then they have some things in common, maybe not everything in common. Or you could even see a situation where if A is a subset of B, which we're going to talk about in a moment, maybe A is smaller and every element of A is found in B. That's another option. We would usually have a different name for this diagram at this point, but just bear with me. I wanted you to have some visualization of what could be happening here. So with that in mind, you can have those notes on your paper, but I'm going to erase it for now. Let's take a look at our first question. So our question says, if A is a proper subset of B, then A is a subset of B. Now notice you don't see the words proper subset. You have to know, based on your notation, that That's what this is saying. That's what this is saying. This is a proper subset. So that's why it's really helpful, I think. Even if you had an open book test, I still think it's helpful to have some of this notation memorized so that you're not having to keep looking back, but you can quickly understand what they're saying. If A is a proper subset of B, then A is a subset of B. Well, just from English, I know this is a little confusing, a lot of words, right? But if someone says that you have a proper item, then wouldn't that still be the same? Well, that's not the best example. But if someone says you have a proper person in front of you, aren't they a person? Yes, by definition, if you have an adjective on the noun, then you still have the noun, even without the adjective. So if you're talking about A being a proper subset, then it has to be a subset. But let's not judge it by English. Let's look at the math here. What did we talk about as far as the definition of a proper subset? We said that that meant every element of A had to be contained in B, where A is not equal to B. Then what was the definition of a subset? Every element of A had to be contained in B, and they could be equal. Okay, so they both are satisfying this definition here. To be a subset, every element of A had to be contained in B. It is. Therefore, this is true. Let me get my black color here for you. So this is a truth. If you're a proper subset, you must be a subset. But if you're a subset, it doesn't mean that you're a proper subset. So keep that in mind. Now in part B, what is this describing here? It says the empty set is a, again, same definition here, same symbol, proper subset. That's right. The empty set is a proper subset of set A. Let's think that through for a moment. We had said in our previous slides that the empty set is a subset of every set, right? But not necessarily a proper subset, because in that one example that we just did in the last slide, the empty set could not be a proper subset of itself because then they'd be equal to each other, which breaks the definition. So in this situation, the empty set is a subset of set A, right? Because we're not talking about the empty set itself here. So this would be a truth for that reason, because the empty set is always an option for any set. Okay. And it's not equal to A, so we're in good shape. What about C? C's a little tricky. Try it on your own and come back and see how you did. Okay, here we go. How'd you do? It said B is a proper subset of B. True or false? Well, if you had the line underneath it, it would have been true. B is a subset of itself, right? But can it be a proper subset of itself? No, this is just like the previous slide where the empty set couldn't be a proper subset of itself because they'd be equal to each other. So for that reason, this is a falsehood again. All right, one more part to this example. Here we go. It says the universal set is a proper subset of the empty set. The universal set is a proper subset of the empty set. So that would mean, okay, that every element, to be a proper subset means, go back to the definition, every element in the set on the left must be contained in the set on the right. So let's say that your universal set has a lot of elements. We know that it's not empty. We talked about that up here. It's not empty, right? So let's say it has the numbers like 1, 2, 3, 4. Let's say that, just for example, let's say that's our universe, okay? Would that set be a proper subset of the empty set? In other words, is every element on the left contained in the right? Well, no, right? Because the empty set has nothing inside of it. So by definition, unless we were talking about a situation where the universal set was empty, then it would be a subset of the empty set. It wouldn't be a proper subset because they'd be equal. So in this case, this has to be a falsehood, right? You don't see any of these elements, let alone all of these elements in the empty set. So this must be a falsehood for that reason. All right. Well, we're all done with our examples for this video. So what did we talk about today? We've talked about subsets, lots of notation, and how to know the difference between a proper subset and a subset. So make sure you have your notes really organized and reach out if you have any questions. Until then, happy practicing. Math is not a spectator sport. I'll see you next time.